systems that we are going to discuss later on in this lecture series is are LTI systems. Okay, they're famous as LTI systems. So a system is both linear and time invariant if it satisfied both the constraints of time invariance as well as linearity. So a system you can say is a linear in both continuous time or discrete time if it possesses an important property known as superposition. So what is superposition? Let's try to understand this. Suppose you have okay, it could be a continuous or a discrete time, doesn't matter. The way you qualify the system as linear for by checking it for superposition is the same. Okay, so it could be a continuous time, it could be a discrete time. So let's assume that you have a certain input, x1 of t, which is applied to the system, and in response to x1t we have an output. Okay, we have an output, let's call this y1 of t. Then for the same system, let's apply another input, call it x2t, which is different from x1t. Okay, so x2t is not the same as x1t. So this yields or produces another output, let's say uh, y2t. Okay, now what you do is, to check if the system is linear, you apply a third input, that is the superposition of the two inputs. Okay, uh, but before that, before we create a third input, that is superposition of the two inputs, that is x3t, it consists of both the prior inputs x1 and x2, like this. We have x1t, and then you add to it x2t as well, and we know what the responses are. Individual responses to x1 and x2 are y1 and y2. So if you add them, the output y3t, if the output y3t is again the superposition of the individual responses y1 and y2, the system is linear. Okay, so if y3t, which is the response of the system to the input, which is x3t, if this is equal to y1t plus y2t, then the system is linear. Okay, so that means the response of the system to the individual inputs x1 and x2, the individual outputs are y1 and y2, and they just got summed up. Okay, so this is superposition. So in general, you can have more than two inputs. It could be x1 plus x2 plus x3 and so on up until xn, and could be an integer up until 100, let's say. So for those number of inputs, if the output consists of the responses to the individual inputs and then superposition of all those responses, in the same way that you get by applying uh, these inputs discretely, if the output is a superposition of all those outputs, the system is linear. This is the property of superposition. Okay, this is additivity or superposition principle. But this is one principle that that helps qualifying the system as as a as a as a linear system. But this is not a sufficient and enough proof for linearity. Another proof is another way to check is by homogeneity. So homogeneity or scaling property, homogeneity and scaling, as it's called in signal and systems language. So homogeneity and superposition are both sufficient and necessary tests to qualify the system as linear. If the system qualifies both the tests, superposition and homogeneity, then these proofs are sufficient enough to qualify the system as linear. So what homogeneity is that? Homogeneity says is that, suppose you scale the input by a certain scalar. It could be a real scalar, it could be a complex scalar. Let's call it a. Okay, any arbitrary scalar, a, positive, negative, fraction, whatever it is, complex. Then the output is supposed to be scaled by the same scalar. Okay, so let's say then similarly my input x2 is scaled by some other scalar, which is b. the output is supposed to be scaled by the same scalar b, which is by2t. Similarly, if you form the superposition of these two inputs, and we know that the output was for a x1t, the output was a y1t, hence this will be a y1t. Similarly, for b x2t, so now if you superimpose and create the third signal x3t, then to this excitation you should have a y1t, b y2t. Okay, so this involves both homogeneity and superposition, okay, both additivity and homogeneity. And you will see that an important consequence of this principle is that suppose a or b or any one of those, okay, let's say if suppose a or a 0, okay, a 0 or b 0, what happens is that the output for corresponding for that corresponding input, so if a scalar is 0, if a scalar multiple, if a scalar multiplying scalar is 0, then the output should be 0, okay, because a is 0. So that means for 0 input, if 0 input leads to 0 output, that means the system does satisfy the principle of homogeneity. So 0 input, if a 0 input leads to the 0 output, the system satisfies the principle of homogeneity. If this is not the case, then you don't need to proceed any further. This is a very straightforward test of testing the system as a linear system. If this is not the case, then the system does not obey the principle of homogeneity. That means you don't need to even check the system for a more involved test of superposition. You don't need to do that. Okay, so it has to satisfy both the principles. So the two principles are superposition and homogeneity. And if the system satisfies both the principles, yes, the system is linear. But if it doesn't satisfy one principle, you don't need to go for another one. Homogeneity is a simple one. Okay, so in words, if what superposition is, so what it says is that if input consists of a weighted sum of several signals, then the output of the superposition is the weighted sum of the responses of the system to each of those signals. Okay, so over here you see it's the same thing. These are the weighted sum of several signals. Over here we have just two signals, but it could be more than that. Okay, so in general it could be a summation. X3 could be ax1 plus bx2 plus cex3 and so on and so forth. So you have a weighted sum of several signals. And then the output is again the superposition of the weighted sum of the responses. Responses are y1, y2, and then they are weighted by the same scalars, a, b, c, and so on and so forth. So they are the weighted sum of the responses of the system to each of those signals. So that is your superposition, okay? So more precisely, let y1t be a response of the continuous time system to an input x1. Similarly, y2 be the output corresponding to x2. So you have over here x1, for x1 the output is y1, for x2 output is y2. So if the system is linear, then the response x1 plus x2 is y1 plus y2. Therefore, the weighted sum ax1 is ay1, where a is any complex constant. It could be real as well. Okay. So this second property is homogeneity. Okay. This is additivity. This is superposition. This is homogeneity. So the first of these two properties is known as the additive property. The second is known as the scaling or the homogeneity property. So the first one is your scaling or additivity property, homogeneity, call it if you might want to. Then the second is the sorry, the first one is the superposition, okay, or the additivity property. The second one is your homogeneity property, where you're scaling the input and get a scaled output. So the two properties defining the linear system can be combined into a single statement. That is the weighted sum of either the continuous time signal. If it's a continuous time system, it handles continuous time signals. So if you make a weighted sum of the scaled or weighted signals, you make a superposition of those, then the output will be the superposition of the individual responses, weighted responses. Okay, these are the weights. A and B are the weights. Similarly, this statement holds for the discrete time system as well. So it's the same thing. You combine the signals. Superposition does hold. Superposition and homogeneity both holds for the discrete time system as well. So A and B can be any complex constant. They can be real. They can be fractions, positive, negative, whatever. Okay. So furthermore, it is straightforward to show from the definition of linearity that xk of n are a set of the inputs to a discrete time linear system with corresponding outputs 1, 2, 3, dot, dot. And the response is a linear combination of these inputs. So this is a linear combination of the input, right? So you have the weighted response. You have weightings a1, a2, and a3. So for individual input signals, you just have the scalars a1, a2, a3, and then if you make an input x of n, okay, you combine all those individual inputs, make another input x of n, then the output should be the weighted response, or this which should come with the same scale a1, a2, a3, which the input was scaled, the sum of all the individual responses y1, y2, y3. So this is a general principle of superposition. Now, a very important fact is known as superposition property, which holds for linear system is in both continuous and discrete time, is that the direct consequence of superposition property is that for linear systems, an input which is zero for all the time, the result is an output which is zero all the time. Okay, so this is what we have talked earlier. So zero input should lead to a zero output. Okay, so what it means is that the scalar is zero. You make a zero input like this, scalar is zero, then the output should also be scaled by zero. So if that is true, then you proceed with the principle of superposition. Not otherwise. If this doesn't hold, the system is nonlinear. Okay, the zero input does not lead to a zero output. Okay, for example, if I say that, if I give you an example like this, y of n is equal to a x of n plus b. Okay, a and b are my multiplying scalars. Okay, let's call it, you can think of a b as real numbers. Okay, positive or negative is not important, but as a consequence of this property, what it means is that if I say if x of n is 0, if my input is 0, well, is the output 0? The answer is no. You can see that y of n is b. So the 0 input is not leading to a 0 output. Okay, b and a are non-zero. A and b are non-zero quantities. Okay, so therefore, for a 0 input, you don't have a 0 output. The system is non-linear. It is non-linear. Although this equation describes, it might be defining a linear equation, but it's not a linear system. Okay, the description of the system which is being defined by this difference equation does not qualify the system as linear, because a 0 input does not lead to a 0 output. System is non-linear, so you have to keep an eye out for such systems. Okay, they might look linear, but they're non-linear, right? So you don't need to proceed any further from here. If you have to, you can show that, okay, y1 is my response to call it an input x1 plus b. So this is my response to a certain input x1 yields y1. Then I have another response y2, which is due to another output which is not equal to x2, another output, another not equal to x1. So this is x2 plus b. So I have two outputs. y1 is a response to x1. Similarly, y2 is a response to x2. Now what I do is I create a third input. Okay? All right. So this third input is the superposition of two inputs. So I'm just trying the additivity properties, okay, without any scalars. So x3 is x1 plus x2. Look what happens. y3 is now equal to, by definition, is now a x3 plus b. Okay, so I just plug this input in the definition of the system to have an output y3, and you see this is equal to a x1 plus x2. Okay, this is in brackets, this is my x3 plus b. Now the question is this equals to y1 plus y2? Can you see that? Is this equal to y1 y2? You see, if you add the y1 and y2, then this is equal to a. You can take the a common and then x1 plus x2. You have this term, but it comes with 2b over here. So y1 plus y2 is again a x1 plus x2 plus 2b. Okay, so you can clearly see that it does not obey the principle of superposition either. It does not validate homogeneity, doesn't obey superposition either. So the idea is, okay, so it's not equal, right? So the system is non-linear. So the idea that I was trying to say over here is that if the system does not obey zero input leading to zero output, does not holds for a system, zero input doesn't give zero output, you don't need to proceed further. I mean, this could be more involved mathematics. This is a simple difference equation, but for more involved description of the systems by differential equations or difference equations for continuous or discrete time systems, just check for zero input leading to zero output. If that holds, then proceed. If this does not, you don't need to proceed. So let's use those ideas. These are the examples from your course text. This is 117. It says that consider a system S whose input and output relations are given by as such. Why this is a continuous time system. So what it does is takes the input xt, multiplies it with the time t, and produces an output yt. Okay, so to determine whether S is linear or not, we consider two inputs. Okay, so similarly, so say that x1 yields y2. X1 is applied to the system. We have an output y1, which is tx1. Similarly, we have another input x2, which leads to y2, which is tx2t due to x2. Okay, note that t is not, you don't have t1 or t2. Why? Because your input is xt. Input is xt, not t. Okay, so y1 is due to x1. Similarly, y2 is due to x2. Then let's make x3 the linear combination of x1 and x2. That is, you make this x3 a linear combination of x1 and x2, but this linear combination involves the weightings or scalings of x1 and x2 by a and b respectively. Okay, so this is my x3. So what I'm going to do is I'm going to introduce this x3 into the system to have y3, and from the definition, if you expand x3 like this, let's see if this y3 is equal to y1 plus y2 or not. So if you expand this, then you can write it as such. Okay, therefore a x1 we have defined before. A t x1 is your y1. Similarly, t x2t is your y2. Now if you substitute these two definitions over here, well, you can reach over here. This is nothing but a y1 then b y2. So in fact y3t, which is tx3, is a y1 plus b y2. Therefore the system is linear. Okay, it does satisfy the principle of superposition and both the homogeneity or the scaling. You see, even you have why we proceeded with superposition was that superposition is not a sufficient proof. Okay, it's enough, but it's not sufficient. You see, a zero input over here does lead to zero output. Okay, so if I have xt as zero input in this case does lead to a zero output. Yt is also zero. So it did satisfy this principle. So we had to proceed with the whole full-blown superposition principle to check if system is linear or not. Okay, so in this case it is linear. Okay, because the output is again the weighted sum of the individual responses y1 and y2, and these are being scaled by the same scalars as we did for the inputs. Okay, the inputs were scaled by a and b, and the outputs are also scaled. The same outputs y1 and y2 in response to x1 and x2 are scaled by the same scalar. So homogeneity and superposition both are verified, and they validate in turn that the system is linear. Okay, let's consider another example and apply the same principles. So let us apply the linearity checking procedure of the previous example to another system S whose input and output are related. So the input and output related by the quadratic. Okay, the output is obtained by taking the quadratic of the input, right? X2t. So let's define x1, x2, x3 in the previous example. So for input x1, we have an output y1, x1 square. Similarly, for x2, we have an output y2, which is x2 square. Then let's have another input x3t, for which the output y3t is x3 square, and this x3t is defined as such, is defined like this. Okay, this is your x3t. X3t is a linear combination of ax1 plus ax2. So x3, I think this should not be here. Okay, there's a mistake. Just note that this is not the case. But basically x3, let me write this down over here. So x3t is your linear combination of two input signals, the same input signals x1 and x2, for which the response was y1 and y2. So this is ax1t plus b x2t. Okay, this is my x3t. Okay, now you see that if you are going to apply x3t to this system, okay, it's like that, this becomes x3 whole square, then you have ax1 plus bx2 whole squared, right? And when you open this square, then there are three terms: a square x1 square, b square x2 square, and then twice ab x1 and x2. So you note that a square x1 square is your is due to the input x1. Therefore, you can write this as a square y1. Similarly, you have due to x2, due to x2, you had an output y2. So you can write this as b square y2t. Similarly, over here a square y1t, and then this term occurs, which does not conveys that this thing is equal to, in either case, this is not equal to the linear combination of ay1 plus ay2. Okay, so you don't have the, you have a third term. We only, if it was linear, you should have two terms, but over here you have three terms, which is not the weighted superposition of the individual responses. Therefore, you cannot have you cannot say the system is linear. It is a non-linear system. It is a non-linear system. The quadratic system is a non-linear system. And you see in this example as well, the zero input did lead to a zero output. So if x of t is 0, if x of t to this system is 0, well, this does implies that your output y of t is also 0. Well, it does satisfy the scaling principle or homogeneity principle, but it does not satisfy the linearity principle. Okay, you see, if to be a little particular about this, you can specify some inputs. So, for example, if x1, x2t, and a and b are such that y3, to show that y3t is not the same as ay1 and by2. For example, if x1 is set to 1, x2 is set to 0, a is to b 0, then what happens? So what I did is I just copied this statement over here. So this was my output. Y3 is due to x3. This is my x3. Okay, this thing is x3 of t. This is x3 of t. So what happens is that you expand this. Okay, you have the same expression, three terms. Now I have for x1, this is 1. X1 is 1, x2 is 0, so you don't need to bother about this term. This term is also gone, this term is gone, this term is gone. So what we are left with is x1 is 1, okay, y1 is 1, so it's a squared. This is 4, so a is 2, right? So a is 2 over here. You see, a is 2. A is 2, b is 0, so don't need to bother about this one as well. So the rest of the terms are 0. This is just 0, which is showing up over here. So a is 2, so you have 2 whole squared. So this is 4. Okay, so y3 is 4. and this is not equal to ay1 plus by2. This is 2. This is not equal to ay1 by2, because if it was to be, then it should be equal to ax1 square plus bx2 square, where a is 2. So 4 is not equal to 2. 4 is not equal to 2. Therefore, the system is nonlinear. Okay. I mean, the proof that we have shown before is good enough for any arbitrary inputs x1 and x2, and the superposition and linearity principle did not hold for this system. So you don't need to take such a specific example. This is just to show what is happening for a specific example. But in general, this proof is good enough to show that the system is nonlinear. Okay, but then again, this is a counter example. This is a specific counter example which shows that the system violates the principle of linearity, that the output y3t, which is due to the superposition of the weighted inputs, is not equal to the weighted sum of the responses of the system. Therefore, the system is indeed non-linear. Okay. All right. Now, uh, let's consider another example, 120 over here. And this is a very, this example is similar to what we have discussed before as well. So we have here a system of, it does define a linear equation, but it does not define a linear system. Why? Because you see, if x of n is 0, if x of n is 0, the output is not 0. If x of n, if I apply x of n as 0, then my y of n is not 0. Then y of n is not 0. In fact, it is 3. Okay, y of n, if input is 0, y of n is non-zero. It is 3. Therefore, it violates the first principle of homogeneity. Therefore, I can qualify the system as simply non-linear. You don't need to even go further, but for curiosity, if you want to, well, then the situation is very similar to what we had earlier. Okay, we showed that this, if for a certain input x1, the output is y1, then for the certain input x2, the output is y2. Um, then you create another input which is a linear combination of x1 and x2. Okay, there are no weightings over here, but I mean, this shows the concept that if you apply this input x3 as an input to the system, then this is ax1 plus x2, which is still not equal to y1 plus y2. So this additivity property does not hold, right? Because y1 plus y2 will have another term 2b. So the system is non-linear. System is non-linear. Okay. So you can show this for this equation. This is the same equation. It's just a is 2 and b is 3 over here. So system is non-linear. Okay. So for the system to qualify as linear, the sufficient and necessary proof is that it must obey the principle of superposition and homogeneity. Homogeneity is simple for the system. The testing is simple by the principle of homogeneity, that is, the zero input leads to zero output. If it does, then you proceed with the principle of superposition. Otherwise, if the system violates homogeneity, that's good enough to say that's a good enough proof you have, and you can qualify the system that it violates the principle of linearity. It's not linear, it's non-linear. Okay, that's all.